Good morning and welcome to the lecture number 17 of the course Water Resource Systems, Modeling Techniques and Analysis. In the last class, I introduced the reservoir operation problem as a multi-stage decision problem, and then we formulated the dynamic programming structure for that particular problem. For example, we are talking about the state transformation governed by the mass balance or the storage continuity in the time period t, starting with a storage S t. The storage S t plus 1 can be obtained by S t plus q t minus R t, neglecting the losses, and we also formulated the recursive relationship. And we started solving a numerical example in which the S 1, which is the storage at the beginning of the first time period, is known to be 0. And the inflows during the 4 seasons are known, t is equal to 1, 2, 3, 4 etcetera are known to be 2, 1, 3 and 2 units. The storage capacity is 4 units, and then you have the benefits associated with release. Now, these benefits, as I keep mentioning, need not be always economic benefits. They may be in terms of the hydropower that is generated, in terms of the crop yield that is obtained, in terms of the flood control that you are able to achieve, and so on. So, these are the benefits which for this example, simple example, we are assuming that they are the same for all the 4 seasons. In general, they can be different for all the 4 seasons, and they may also depend on the storages. All right. So, for the stage number 1 we solved. So, I will just rush through the first stage calculation. Please refer to the previous lecture. So, in stage number 1, what is the question we are asking? If S 4 is known, S 4 is the storage at the beginning of the 4th time period number 4, which corresponds to stage number 1. So, we write F 4 1, 4th time period, that is time period is equal to 4 and n is equal to 1, the stage number 1. Because you do not have anything else to look beyond, it is simply maximize B 4 of R 4 and R 4 is the decision. Remember here that the storage plus inflow minus the release must be less than or equal to the total capacity available, which is 4. And the R 4, which is the decision that you are making, will be taking on values between 0 and S 4 plus Q 4, because S 4 is the storage available plus Q 4 is the inflow that is coming there in that particular time period, and therefore, this is the total amount of water available. You can make releases from 0 to S 4 plus Q 4. Now, this is what we saw in the previous lecture. I encourage you to go to the previous lecture, where I have discussed at length the formulation of the dynamic programming. Then we also solved for stage number 1 in the previous lecture. Stage number 1 corresponds to time period 4, which means Q 4 which is given is 2. We ask the question, if S 4 is equal to 0, what should be my R 4? So, if S 4 is 0, R 4 can be 0, 1 or 2, because the total water available is 0 plus 2. So, you can either release 0 or 1 or 2 and so on. So, if you release 0, you get a benefit of minus 100, 1 250, 2 320 etcetera, and you obtain the maximum of these, and that corresponds to R 4 is equal to 2. Like this we keep going. When you come to 3, you see that we start with R 4 is equal to 1 and not R 4 is equal to 0, because 3 plus 2 is 5, which is more than the storage capacity 4, and therefore, we start with R 4 is equal to 1, we go up to 5. So, R 4 can take on values up to 5. Similarly, when we come to S 4 is equal to 4, 4 plus 2 is 6, and therefore, minimum of 2 has to be released. Remember, the release also includes the overflows, that is the excess flow or the spill over and above the storage capacity is the overflow, and that includes this. Therefore, for 4 we go up to 6. So, this is what we did in the previous lecture, and then we went to stage 2. In the stage 2, we are in t is equal to 3, period t is equal to 3, and stage is 2. We are asking the question, if S 3 is known, that means if S3 is equal to 0, 1, 2, 3 etc., what should be my R3? So, we are making a decision on R3 such that the total benefit starting with this particular stage and all the previous stages included. In this particular case, there is only one previous stage. So, the previous stages, the total benefit should be maximum. And R3 again takes on values between 0 and S3 plus Q3, which is the total water available. Q3 is known and S3 is the particular S3 value for which we are solving this particular recursive relationship. S3 is such that S3 plus Q3 minus R3 should be less than or equal to the total capacity 4. Now, this is where we stopped in the previous lecture. Now, we will continue the example. So, we will solve the recursive relationship for various values of S3 and obtain the corresponding R3. The question we are asking at this stage is, if S3 is equal to 0, what should be my R3? If S3 is equal to 1, what should be my R3? And so on, such that the total benefits accrued up to that particular time period in the backward direction, including all the other time periods, is a maximum. So, let us say S3 is equal to 0, R3 can be either 0, 1, 2 or 3. If R3 is 0, remember in the last class I also told how to set up these columns. Just look at these terms here and then set up the columns. So, if R3 is 0, then I get a benefit of minus 100, and if R3 is 0, I will have the end of the period storage as 3, because 0 plus 3 minus R3, which is 0, 3. And corresponding to this, what is this? This is a storage at the beginning of fourth time period equal to 4, and for time period equal to 4 we have already solved, and this defines S3 plus Q3 minus R3 defines S4, which is in fact the state variable for stage number 1. So, S4 is my state variable for stage number 1, for which we have already solved. So, corresponding to this value of S4, we go back to the stage number 1 calculation, and it says 520 is the F41 corresponding to S4 is equal to 3. So, that we take it as 520, and these two together will give you a total benefit of 420. Similarly, if R3 is 1 starting with S3 is equal to 0, your benefit accruing B3 R3 is 250. Because R3 is 1, your S3 plus Q3 minus R3 will be equal to 2, that is 0 plus 3 minus 1, that is equal to 2. Corresponding to 2, you go back to the previous table and pick up the optimal objective function value, which is 520, and that is the 520 that you put here. 520 plus 250 is 770, and so on. That like this you calculate. So, 420, 770, 800, 800. Out of these you will pick up the maximum value, because your objective function is maximization. So, this is 800. So, this is what defines your F3 to S3, which means for a given S3, in this particular case S3 is 0, for a given S3, what is the total maximized objective function value up to that point is what we are answering here. So, this will be 800, and the R3 star is the corresponding release which results in this particular objective function value, that is either 2 or 3, both of them result in a objective function value of 800, and therefore, R3 star is 2 and 3. Similarly, you come to 1 now, that is we are asking the question, if S3 is equal to 1, what should be the optimal release. So, if S3 is equal to 1, we have a total amount of water of 1 plus 3, 4. So, you can go up to 4, 0, 1, 2, 3, 4. And if you go with 0, 1 minus 0, 4 is left, 1 plus 3 minus 0, 4 is left. Then if you go with 1, 1 plus 3 minus 1, 3 is left. 1 plus 3 minus 2, 2 is left, and so on. So, 4, 3, 2, 1, 0. This is the amount of water available for the next time period, which is S4. And corresponding to S4, you would have solved earlier, pick up the corresponding objective function values from the previous stage computations, and then add these two, the immediate benefits at this particular time period plus the optimized benefits of all the time periods until this particular time, in which in this particular case it is only one time period. So, 520 minus 100, 420, 520 plus 250, 770, and so on. So, you will get values like this. Then pick up the maximum of that will be 960, that corresponds to 3, which is R 3 star is 3, which defines R 3 star to be 3. Then you go to 2, do the same calculations again. Remember, we are starting with a release of 1 and not as 0 earlier, because 2 plus 3, 5 is 1 unit above the capacity, which is 4, and therefore, the minimum release that you have to make is 1. So, 2 plus 3, you go up to 5, 1, 2, 3, 4, 5. You can make a maximum release of 5. Do the same calculations as we did earlier, and then obtain R 3 star as 3 or 4, and the corresponding objective function value is 1000. Go to 3, 3 plus 3 is 6. So, a minimum release of 2 has to be made because the capacity is 4. Then you can go up to 3 plus 3, 6. So, 2, 3, 4, 5, 6. 2, 3, 4, 5, 6 correspond to these releases, and similarly you obtain the next time period storage 3 plus 2, 3 plus 3 minus 2, that is 4, 3 plus 3 minus 3, 3, and corresponding to this go to the previous table, pick up the maximum objective function value. These are the maximum objective function values, and sum these up, you will get this, pick up the maximum, and so on. Like this you keep on continuing until S3 is equal to 4. So, this completes the stage number 2 calculation. So, stage number 2 corresponded to period number 3. Now, we go to the next stage, stage number 3. So, remember, in stage number 2 essentially what we did is that we connected what we have already solved. This is t is equal to 4 and t is equal to 3, n is equal to 1, n is equal to 2, and stage number 2 we dealt with t is equal to 3. We were here, we said if the storage at the beginning of the time period 3 is known, then what should be my release R 3 such that the total objective function value, including what we have already solved for stage number 1, t is equal to 4, the total objective function value is maximized, and this is where we are using the Bellman's principle of optimality. Because we have already solved for various possible values of S4, we know that the moment you know S4, we know what is the optimal objective function value, and we get this S4 from the storage transformation equation, namely S3 plus Q3 minus R3 will define the storage at this particular time, neglecting losses, and the moment we know the storage, we know what is the optimal objective function value for that, and then these two we add and get the optimal objective function value at stage 3, and we also obtain R 3 star corresponding to each of the S3. So, this is what we did in stage 2. Similar computations we do for stage 3. Stage 3 will be much like stage 2 calculations. So, in stage 3 we are dealing with time period t is equal to 2. So, t is equal to 2, n is equal to 3, that is stage number 3, and Q2 is given, Q2 is 1. So, we write the recursive relationship F2 3, this is time period and this is the stage, is equal to maximize B2 R2, which is the immediate returns from that particular time period which is included now, corresponding to a release of R2, plus this term here is from the previous stage. From previous stage table. So, starting with S2, making a release of R2 for a given Q2, we obtain S2 plus Q2 minus R2 as the storage at the beginning of the next time period t is equal to 3, and associated with that we have solved already. If we know the storage at the beginning of the time period 3, we know what is to be done, what is the particular optimal objective function value. This we have done in the previous stage calculation. So, we pick up the optimal objective function value corresponding to S3 plus Q3 minus that is S2 plus Q2 minus R2, which defines S3 from the previous stage calculations. That is what we do here. S2 is that particular value of S2 for which we are doing this calculation. R2 is a search that we are making, and Q2 is known and it is constant, and we are ignoring losses. So, that is what we do now again. Alright. So, what we then do is similar to what we did in the stage number 2, we set up the recursive relationship. This is F2 3, that is time period 2, stage 3, S2, which is the storage at the beginning of time period 2, is equal to maximize B2 R2, which is a return associated with a release of R2 plus the optimized objective function value in the previous stage corresponding to the storage S2 plus Q2 minus R2, and these two constraints are similar to what we did in the previous stage. So, we start with S2 is equal to 0, 0 plus 1. So, you can go up to 1. So, R2 can be either 0 or 1. If R2 is 0, the benefit is B2 of R2 is minus 100. If R2 is 1, it is 250. If R2 is 0, then 0 plus 1 minus 0 is 1. Corresponding to 1, you go to the previous table, corresponding to S3 is equal to 1, you pick up the objective function value directly, 960. So, that is 960. So, 960 minus 100, that is 860. Similarly, if S2 is equal to 0 and R2 is equal to 1, you are left with 0 for the next stage, because 0 plus 1 minus 1, that is 0. Go to the previous stage calculation, corresponding to 0, it is 800, the objective function value is 800. Put that 800 here, 800 plus 250, that is 1050. In case of any doubts, you always refer to this equation. What we are doing is, we are calculating for each possible value of R2 for a given S2, we are calculating the terms B2 R2 plus this term. So, this term we are picking up from the previous table, and we are calculating this term now B2 R2 plus F3 etc. Then among all the possible values of this term here corresponding to a given S2, we pick up the maximum value. So, that is what we get here as 1050, and R2 star is the associated value of R2, which results in this particular objective function value. In this particular case, it is 1. Therefore, we write 1. One more computation I will show you, and then you can verify all the other tables. So, this is what we do. Let us say that S2 is equal to 3. S2 is equal to 3, you have Q2 is equal to 1. So, 3 plus 1, 4. You are still within the capacity. Always check that the R2 should be such that the end of the period storage that you get here should be a maximum of 4. So, 3 plus 1 minus 0 is 4. Corresponding to 4, you pick up from the previous table the objective function value, from the previous stage calculation objective function value, which comes to be 1040. So, you write 1040 here, and 1040 minus 100 is 940. Similarly, let us look at another R2 value 4 here, 3 plus 1 minus 4, that will result in value of 0 here. and corresponding to 0, you go to the previous stage calculation and pick up the objective function value, optimal objective function value 800. Remember, all of these other values you do not worry, simply look at the optimal objective function value corresponding to a given S3 in this particular case. So, this is 800 and that is 800 that you put somewhere here, here 800 you put. So, 800 plus 520, 1320, so you get 1440 and so on. Like this you complete for all possible values of S2. So, when you do the third stage calculation, what is the question that you answered? We answered the question, if at the beginning of the third stage, that is stage number 3, which corresponds to period number 2 now, if the storage at that beginning of the time period 2 is known, what should be my R2 such that the total benefit inclusive of period number 1, period number 4, period number 3 and period number 2 is maximized. That is the question that you have answered. So, you are proceeding in the backward direction and then you are optimizing until that particular point where you stand, which is at the beginning of time period 2. So, this is what we answered in this stage. Now, we come to the fourth stage, that is stage number 4. It is T1 is equal to 1 now and n is equal to 4. We have to solve for values of S1. What are the values of S1? The problem statement is that you have fixed the storage at the beginning of time period 1. So, this is T is equal to 1, 2, 3, 4 and we proceeded in this direction. We have now reached this point. This point the storage is known. So, S1 is equal to 0. This is given in the problem. So, you solve for S1 is equal to 0 because that is given. So, S1 will not take on any other values, unlike your S2, S3, S4 etc. It will take on only one value, namely S1 is equal to 0 and all other conditions remain the same. B1 of R1, which is immediate return from that particular time period 1, S1 plus Q1 minus R1 will define the storage at the beginning of time period 2 here, and we have already solved for that particular stage. Essentially what we have done is, at the time period 2 we would have solved in stage number 3, 1, 2, 3, we would have solved for all of these periods together. So, we just relate from this stage, from the beginning of this time period, we relate with what we have already solved in the previous stage, which included all other periods. So, this is what we do in the stage number 4. So, Q1 is given as 2 and we will solve this for S1 is equal to 0 because S1 is 0, S1 is 0 in the problem. So, S1 is equal to 0. For all other stages, we solved for all possible values of the storage at the beginning of that particular time period in that particular stage. Because we did not know the storage, we asked the question in other stages, if my storage at the beginning of this time period is so much, then what should be my optimal value? Whereas, when we come to time period 1, we know that the storage of the at the beginning of the time period is 0. So, we solve the problem for stage number 4, which corresponds to t is equal to 1, time period t is equal to 1 for the given value of storage. So, S1 is 0 and Q1 is 2. So, R1 can go on up to 2, R1 can take on values up to 2. So, 0, 1, 2. If R1 is 0, then these are the benefits you can pick up from the table for time period t is equal to 1. The benefits remain the same for all the time periods. So, it is minus 100, 250 and 320. If R1 is 0, starting with S1 is equal to 0, 0 plus 2 minus 0, which is 2. This defines the end of the period storage or the beginning of the period storage for next time period, this will be actually S2. So, this will be S2 and corresponding to S2 we have already solved in the previous stage. So, corresponding to that you will pick up the previous stage optimal value. Say for example, S1 plus Q1 minus R1 is equal to 2. Go to the previous stage calculation, look at S2 is equal to 2, pick up the value which is 1280 and that is what we write here 1280. Similarly, 0 plus 2 minus 1 is 1. So, go to the previous stage value, look for 1, that is S2 is equal to 1, the optimal objective function value is 1210. So, you write that 1210 here. Similarly, for 0 it is 1050 and you sum these up because that is sum this and this 1280 minus 100 1180, 1210 plus 250 1460, 1050 plus 320 that is 1370 and so on. And then pick up the maximum that results from these, which means essentially what we are saying is, given that S1 is equal to 0, whether my R1 should be 0 or R1 should be 1 or R1 should be 2. And this says that the maximum value resulting is 1460 and therefore, your R1 should be 1. What is this maximum value? This is the maximum objective function value arising out of solution for all the 4 time periods, t is equal to 1, 2, 3, 4. All of these are included because you are relating it with the previous stage calculation, which included all these 3 periods optimal objective function value. So, this objective function value here, that is F2 3 of S1 Q1 S1 plus Q1 minus R1 has included the all the other periods also up to that point, and this is where we are actually using the Bellman's principle of optimality. That is, what we are saying is, starting with the known value of storage here, you proceed in an optimal way, optimal manner until the end of the horizon, until all the stages are completed. This is what we have done here. Now, we have solved for the last stage, which is t is equal to 1 or stage n is equal to 4. At this point now, we start tracing back the solution, because you need the releases associated with period number 1, 2, 3 and 4. The last stage calculations gave you the release for t is equal to 1, which is the time period 1. So, what it says, because you are in S1, you release 1. This is what it says, nothing else. And it also says that your optimal objective function value until the end of the time horizon will be 1460. Now, we have to trace back now. How do we trace back? In period t is equal to 1, you started with the storage of 0, you got an inflow of 2. So, 0 plus 2 minus 1 is the release that you made. So, 0 plus 2 minus 1, which is 1, will be the storage at the beginning of the next time period, which is 2, t is equal to 2. With this storage, you go back to the previous stage calculation, which correspond to period t is equal to 2, and for this particular storage that you obtained, you look up the corresponding R1 star, R2 star in that case, and then again do the mass balance, look at the storage at the end of that period, which is t is equal to 2, period t is equal to 2, and that defines the storage at the beginning of the time period t is equal to 3. Go to the time period 3 calculations, which is the stage 2 calculations, look corresponding to that particular storage, you look up what is the optimal solution, apply that optimal solution for this particular time period, come to this time period, beginning of the time period, go to stage 1 calculation, which corresponds to t is equal to 4, apply that particular release in this particular time period, and thus you get release during time period 1, 2, 3 and 4. So, this is how we trace back the solution after we solve the last time period. Relate this with what we did in the water allocation problem, it is much similar. simply arrive at the last stage calculations and then keep applying the optimal decisions, and in the forward direction now you will obtain the traced back solution. Let us do that now. So, R 1 star is 1, which means 0 plus 2 minus 1. So, you will get S 2 is equal to S 1 plus Q 1 minus R 1 star. S 1 is 0, Q 1 is 2, R 1 star is 1. Therefore, you will get S 2 is equal to 1. Go to stage 3 calculation and look at what is the decision corresponding to S 2 is equal to 1. So, we will go to stage 3 calculation and S 2 is equal to 1. It says R 1 R 2 star must be 1. So, we will implement that. R 2 star is 1. So, that is S 2 which was 1, Q 2 which is given to be 1 and minus R 2 star. R 2 star is 1 from the table corresponding to the stage 3. So, 1 plus 1 minus R 1, that is equal to 1. With this one now you go to stage 2 calculation, which means S 3 is equal to 1. So, look up for the table containing S 3 is equal to table containing S 3 and S 3 is equal to 1. It says my R 3 star must be equal to 3. So, simply implement that R 3 star is equal to 3 and say S 4 is equal to S 3 plus Q 3 minus R 3 star, 1 plus 3 minus 3 which is equal to 1. This defines S 4 which is the storage at the beginning of the time period 4, which corresponds to stage number 1. Go to stage number 1, look for S 4 is equal to 1. So, stage number 1 we went and look for S 4 is equal to 1. It says R 4 star should be 3. So, R 4 star is 3. So, this is how we trace back the solution after we have solved the problem completely. At the last stage you get the optimal decision, and from that optimal decision you trace back the solution. In all discrete dynamic programming problems of the type that we are talking about, this trace back will be necessary to obtain the optimal decisions at various stages. So, the optimal release sequence for the problem is you have 1, that is time period t, you had the solution 1, 1, 3, 3. So, which means that the release in the first time period is 1, second time period is 1, third time period is 3 and fourth time period is 3. This is how we obtain 1, 1, 3, that is 1, 1, 3, 3. This is the sequence, optimal sequence of releases. And the maximum net benefits resulting from this is 1460, 1460. This is the final objective function value. Remember, you should not add now at this stage 1460 plus what you got here corresponding to that particular S 2 and so on. You should not add these objective functions again, because you have already added up all of these. So, these terms finally, when you get this term, all of these objective functions values, individual objective function values have been added, and this is the final optimal objective function value. So, that is the objective function value that you get here. So, this is a classical reservoir operation problem when you have discrete states of storage, and inflows are also taking on discrete values, and release therefore, will also take on discrete values, and we have ignored the losses here. Now, this is a typical problem where we have specified the storage at the beginning of the time period. Let us say what we did here is that the storage at the beginning, some subtle points that you must remember now. You had 4 periods S 1 and this is the storage at the beginning of the time period. So, this was known in the particular case, and this was left free, that is storage at the end of the 4th time period. Let us say this is 1, 2, 3 and 4. So, the storage at the end of the fourth time period was left free. And therefore, when you solved here for t is equal to 4, this was t is equal to 4, t is equal to 3, t is equal to 2 and 1. So, when you solved for t is equal to 4, what is it that we did? We started with if S4 is 0, S4 is 1, S4 is 2, etc. Like this we went up to 4. Because this end was left free, we did not specify any storage at the end of the time period 4. Now, S1 was set to be 0. Similarly, S1 could have been set to 1, set to 2, etc. So, this boundary condition here we could have fixed based on some requirements. Let us say that we would have said S1 should be 1 at this point. Now, the storage continuity equation always relates the next time period storage with the previous time period storage. So, we are proceeding in the backward direction here. Whatever the storage that we got here, we can relate it with the storage at the beginning of this time period using this, and that is why the backward recursive relationship is advantageous for this particular problem. If you need to move forward, then you have to express ST, it becomes messy because you will be solving ST in terms of ST plus 1, whereas the continuity is in the forward direction. Therefore, for reservoir operation problems, the backward direction is advantageous. There is one more issue here. Now, we fixed S1 to be 0. Let us say that we do not put any constraint on S1, we simply leave S1 also free, in which case you should solve this problem for S1 taking on value 0, 1, 2, 3, 4 and so on. What is the question that we are asking there? That you are saying that we do not want to put any constraint on what should be my initial storage. We leave everything free and you give us the optimal operating policy. So, we solve for 0, 1, 2, 3 and 4 even for S1 and then state if your S1 is so much, this is the policy. If S1 is so much, this is the policy and so on. So, we specify the policy as a function of the storage at the beginning of the first time period. This is what we do typically in the applications. When we go to the applications, you will appreciate the problem, but this is a subtle point that you must remember. S1 need not be fixed. Because you are specifying the policy can be specified as a function, as a function of the initial storage at the beginning of the first year. Then the other thing is, along with fixing S1, we may also state S5, which is the end of period storage at 4. At period 4. You understand this slightly clearly, because in the applications these things become important. Let us say t is equal to 4, t is equal to 3 and so on, like this we went. What we did was, we started the computations at this point, this was stage number 1. So, we said the storage at the beginning of this time period is known, or we solved it for various values 0, 1, 2, 3, 4 etc. for the storage at the beginning of this time. We did not worry about what is the resulting storage at the end of that time period. In many situations, we may fix this storage also, that is storage at the end of the time horizon must be at least so much. Let us say that you are talking about over the year storages, in which case you would like to maintain a minimum amount of water in the reservoir at the end of the year. So, we may state that this storage is also fixed, in which case what you will solve here? Your Q4 is known. So, your S5, which is the storage that results from this particular S4 for this Q4, will be fixed. Let us say that we fix S5 is equal to 2 or some such thing. Then the way you solve is, in this example that I solved, when the end of the year storage was left free, what did we do? We said S4 can be either 0, 1, 2, 3 and 4. When we fix this storage, end of the period storage, you choose only those particular values of S4 for this given Q4 that result in exactly S5 is equal to 2. So, your S4 and R4 combination for this given Q4 should be such that the combinations will result exactly in that particular value of 2. So, while you may have 0, 1, 2, 3, 4, your R4 values must be such that you will result S5 is equal to 2. Similarly, you may say that S5 should be greater than or equal to 2. Then you can have those particular values of S4 and Q4 and R4, Q4 is known of course, such that the resulting storage value will be greater than or equal to 2, and so on. So, you can fix several boundary conditions in the initial stage as well as in the final stage. You can fix these boundary conditions when you are looking for the combinations of S4, R4, S3, R3 and so on. You must make sure that you will use only those particular combinations which are feasible in the sense that they meet the conditions that you have set for the problem. So, in any given table, you should always look at whether you are meeting all the conditions or not. In fact, we did this in our calculations, because every time we were checking whether the resulting storage is in fact below the capacity of the reservoir or not. That is how we pick the R combinations, that is the release combinations along with the given S values. So, there are several subtleties you should start applying, and then you will realize, keep all these subtle points in mind in reservoir operation. So, we solved two problems using dynamic programming. One was the water user allocation problem, that is a known amount of water allocated to a number of users. The second one is the reservoir operation problem, which is a classical problem in water resources, where discrete values of storages are concerned. Now, in the remaining time of this particular lecture, I will introduce two more problems, but I will not discuss these problems in great numerical details as I did for the other two problems. Now that you are aware that you need to define the state variable, you must identify what is the stage, then you must also identify what is the decision variable, what is the state transformation from one stage to another stage. Once we are able to write all of these, then the problem is quite simple. So, for any given problem, you must be able to identify these four requirements. What is the stage, what is the state variable, what is the state transformation from one stage to another stage, and what is the decision variable. So, let us look at two more problems in the remaining time that I have today. One is another important problem in water resources, namely the capacity expansion. So, we look at the capacity expansion problem. What is this problem? You have large water resource systems in place. You are developing large water resource systems, and these will have several components. For example, you may have a reservoir, you may have a canal network, you may have a hydropower plant, you may also have lift irrigation schemes and so on. So, a water resource system, when you are developing it, it involves developing several components, and these components need to be added over a period of time. So, at the beginning of this time period t is equal to 0, when you are standing now, you need to make a decision on how do we expand the capacity. That is, at t is equal to 0, you have a certain capacity. By capacity, I mean it need not be only reservoir capacity. You may have built the reservoir, you may want to expand the canal network over a period of let us say 20 years. You may want to expand the hydropower, you may want to expand the lift irrigation scheme and so on. So, water resource systems by their very nature are large in size, large in space, and therefore, they take a significant time for complete development, and it is important for us to assess how we are going to expand the capacity as time progresses. This is the problem of capacity expansion. So, we are asking the question starting at time period t is equal to 0, how do we plan for capacity expansion, knowing that we need to invest a certain amount of money at various times across. Let us say you are looking at a time horizon of 25 years. You have a given capacity at this particular time period. You are asking the question, over the next 5 years, what is the capacity that I need to expand? From year number 5 to 10, what is the capacity that I need to put? 10 to 15, what is the capacity that I need to put, and so on. Knowing at the beginning itself that I need a certain capacity at the end of 5 years, a certain minimum capacity at the end of 10 years, certain minimum capacity at the end of 15 years, and so on. So, we specify a priori the minimum capacities that are required. Remember, this capacity you relate not just necessarily with the storage capacity. I keep repeating that it has to do with several component capacities. For example, you are talking about water supply system, stage 1 water supply enhancement, stage 2 enhancement, and so on. So, these capacity expansions can be various physical component expansions, all of which require significant investment, and you are making the investment into the future, but you are making the decision now, and therefore, you need to calculate the value of the investment that you make in future at the present time. The present worth of the investment that you are going to make in the future is what is important. So, we will just look at the problem. You understand the problem correctly. I will also state the formulation, but we will just rush through the solution itself. So, we will take this example. There is one existing capacity and you are specifying the minimum required capacity at each time horizon. Let us say that this is 5-year period, this is 5-year period, 5-year, and so on. So, from time t is equal to 0, this is 5, this will be 6 to 10, this will be 11 to 15, then 15 to 20, and so on. So, let us say that you want to expand the capacity in this particular manner. That means, you are saying that at the end of the first 5 years, my minimum required capacity is here. At the end of second time period, my minimum required capacity is here, and so on. At the end of this time horizon, I want to achieve the full capacity expansion, and this is the point that I want to reach. Whether we should reach along this line or along this line. For example, I may provide a capacity much more than what is required here, much more than what is required here, much more than what is required here, etc., such that I come here, such that the total investment that we make across all of these time periods is a minimum. And we are talking about the present worth of investment. So, we ask the question, given the existing capacity, what should be my expansion during the first 5 years, next time periods, next 5 years, next 5 years, and so on, such that the present worth of investment which we are in fact making in the future is a minimum. This is a problem, and in this particular example, once you understand that statement of the problem, the example is pretty straightforward. We want a minimum additional capacity. It has a existing capacity of 100 units. We want to reach a capacity of 200 units in the next 20 years. At the end of each of 5 years, we need a minimum capacity here, required capacity. That means, we are specifying these points now. So, the required capacity at the end of the first 5 year is 20 units, which means starting with 100, we want 120. Starting with 100, we want 140, starting with 100, we want 160 minimum capacity, and at the end of the 20th year, we need a capacity of 200 units. We have the present worth of the investments. Now, do not worry too much about the economic aspects of it. Simply assume that these values are the values that you will be investing in terms of their present worth, which means what? Although you may have invested for a capacity of 20 at the beginning of 6th year, the value should be reckoned at this present time, and like this, and therefore, you can see that if you invest for additional capacity of 40 for example, the amount that you may have to invest right now is 150, but if you invest at the end of 5 years, which is at the beginning of 6 years, the same value will be less, because we are talking about the present worth, which means the first 5 years you are not spent and you are going to spend it at the beginning of the next 5 years, at the beginning of the sixth year, and therefore, this value, this money is with you now, you have not spent it, and therefore, this value will be lower and lower as you progress more into the future for the same amount of money. So, for the same capacity expansion, as you progress in time, these values are small. Anyway, these are subtleties that you do not worry right now. Right now, we will focus on how we formulate this problem as a dynamic programming problem and then solve it from stage to stage. So, the question that we are asking now is, starting with a known capacity of 100, in stages of 5 years, how do we keep expanding the capacity such that the minimum required capacity at the end of each of the 5 years, which is specified, is attained. Now, this is formulated as a dynamic programming problem. This is t is equal to 4, which means you have a 20-year horizon, and each of these time horizons that I showed constitutes a stage here. So, this is stage number 4, stage number 3, stage number 2, stage number 1. T is equal to 1, t is equal to 4, t is equal to 2 and so on. If you are proceeding in the backward direction, it will be n is equal to 1, stage is 1, stage 2, stage 3 and so on. So, this is how we progress, n is equal to 1 and so on. So, stage is the period during which a decision on capacity expansion is required. Then state variable is capacity at the beginning of the time period, and decision variable is capacity expansion during the time period. So, these three definitions you must remember now. Okay, there is one more point here. When we specified these values here, you look at this, the minimum capacity that has to be expanded is specified from here, 20, 40 and so on. So, which means 120, 140 etc. So, when you come to 6 to 10 years, the minimum capacity would have been already 120 and what you require is 200, maximum is 200. So, you go up to only 80 here. Similarly, when you come to the next stage, you go only up to 660, next stage you go only up to 40 and so on. So, that is how the present worth additional capacities are known. Now, when you are standing at the stage number 4, this is t is equal to 4, you do not know what is the current capacity at this point. So, you will ask the question, if my current capacity is so much, what should be my decision for the next time period, is the question that we will ask. So, S4 can start from 160 because the minimum required capacity at the end of stage 3 was 160. You see here, this was 60, you had 100. So, minimum of 160 should be there. Therefore, S4 cannot be anything less than 160, it has to be 160 and it can go up to 200. So, the question that we ask is, if S4 is 160, if S4 is 180, if S4 is 200, what should be my X4, such that the minimum cost is, the cost associated with that is minimum and so on. Like this, you go to next stage then. Next stage, it can go on between 140 and 200, because 140 is what you would have achieved earlier, and at the end of the time period you should have 200 maximum. So, S3 plus X3 must be 160. What is X3? X3 is the decision that you make on the capacity expansion at time period t is equal to 3. So, this is what we do for stage number 2. Then you go to much like the way we did the reservoir operation. In fact, this is very similar to the reservoir operation problem. You just verify all of these. The question that we are asking is, if S3 is known, what should be my X3? If S2 is known, what should be my X2 and so on. So, much the same way as we did earlier. We keep on computing the cost for immediate expansion and the optimized cost for the state resulting from this S3 and this X3. In this particular case, it will be only S3 plus X3, because we are adding the capacity S3 and X3. Like this, you go to stage number 1. In stage number 1, it is given that S1 is equal to 100. It is exactly same as the reservoir operation problem. The existing capacity at the beginning of the time period is known to be 100. So, you solve only for 100, you get the optimal objective function value as 250 and the associated values as 40 and 60. So, what does this say? It says that starting with 100, you can go either to 40 or to 60. Now, when you trace back the solution, you trace back for both 40 as well as 60. If you trace back for 40, this is what it says. Start with 100, expand 40, you get 140. For 140, expand 0 in the next stage, you get 140. For 140, you go expand 60, you get 200, and 200, 0, 200. So, finally, you achieve a capacity of 200 right at this point, and the associated objective function value is 250 units. Corresponding to 60, because you can trace back for 40 and 60, corresponding to 60, the solution is 100, 60, you end up with 160, 0, end up with 160, 0, end up with 160, because 160 was necessary at the beginning of the fourth stage, and then 160, 40, 200. Both of these lead to a optimal objective function value of 250. So, this is what we did in capacity expansion problem. Now, there is a last problem that I would like you to understand. Many situations arise where you look at shortest route problems. Typically, in pipe networks and so on, you may arrive at such a problem. I will just explain this problem, and this problem solution is available. You can just look up this. From the source, you want to go to destination, and there are various paths available. From here, you can go either to B1, B2 or B3. From here, you can go either to C1, C2 or C3. From here, you can go D1, D2 or D3 and finally reach the destination. So, we define for this problem the stage 1, stage 2, stage 3 as being here and being here and being here. So, the question we ask is, we proceed in the forward direction. In this case, you can also proceed in the backward direction, and I encourage you to look up solve this problem also in the backward direction. We ask the question at stage 1, if I am in node B1, from where I should have come, if I am in node B2, from where I should have come, etc. Node stage number 1 computation is trivial, but when we go to say stage 2, let us say, if I am in a given stage, whether that is C2, if I am in a given node C2 in stage 2, whether I should come from B1 or B2 or B3, such that the total distance covered from the source up to this point is a minimum. Similarly, if I am in D3 in stage 3, I ask the question whether I should have come from C1 or C2 or C3, such that the total distance covered from the source up to this point is a minimum. Like this, for every stage, we keep on asking the question, in this stage, if I am in the particular node, from where I should have come in the previous stage, such that the total distance covered from the source up to that point is a minimum. So, the state we decide as the node in stage n, and the decision that we are making is node in the previous stage n minus 1, from where you have reached this particular node. So, state variable is decided, state decision variable is decided. What is the state transformation? State transformation is simply the decision itself, that is you will define x n that defines the state during the previous time period. So, like this, for example, stage 1, you look at these and minimize this, and you will get, you are answering the question, if S1 is equal to B1, then my x 1 star is A. So, we will continue this discussion in the next class, but I will not revisit this problem. The problem solution is available in the handout. It is much similar to the earlier two problems that we have covered. I encourage you to solve this problem also in the backward direction. The problem solution that I am providing here is in the forward direction. You also continue in the backward direction and then make sure that you get the same result. So, thank you for your attention. We will start with the next topic in the next lecture.